All right, so next up we have Friedel-Crafts acylation. So an acyl group is just going to be a carbonyl. But on the other side is this R group. This R group has to be some kind of alkyl halide. Or my bad, just some kind of alkyl group, not a halide group, just an alkyl group. So methyl, ethyl, terbutyl, something like that, right? Can't be an ester, can't be an amide, something like that. Has to be alkyl. And so what we can do here is we can take our benzene ring, we can add what's known as an acid chloride, add some catalyst, and attach it onto our benzene ring. And again, the function of this chlorine and the AlCl3 is to make our compound more electrophilic. If you haven't noticed, that's the theme of this part. Let's see how this happens. So what's going to happen here is this carbon-chlorine bond is going to break, and the electrons are going to go to our Lewis acid catalyst, our AlCl3. And so that'll form our AlCl4-, but really what we're interested in is the other component, where we now have a positive charge on this carbon, and then an R group down below. What we can then do is we can take a lone pair from this oxygen and simply move it down. And so what we have here is a resonance structure. So the reason that we can form this intermediate ion is because it's resonance stabilized. Note that the resonance structure on the right is better, even though the positive charge is on the oxygen. And it's better because the structure on the right has a filled octet, whereas this one right here, the central carbon does not have a filled octet. This is called an acylation ion, right? And it acts as our electrophile. And so the rest of the mechanism is basically the same as what we've learned. We have our benzene ring. We have our acylation ion. Our benzene ring acts as the nucleophile, attacks our electrophile. Then we just go ahead, break this carbon-oxygen bond. That way we're not breaking the octet rule. Then we're left with our sigma complex in the middle, and then we're going to deprotonate this and regenerate our catalyst. So the aluminum chlorine bond is going to pick up the H. The carbon hydrogen bond is now going to become a carbon-carbon pi bond. And now we've added an acyl group to our benzene ring. So why is this kind of better than the Friedel-Crafts alkylation? For a number of reasons. One, there's no rearrangement. And that's the major weakness of the Friedel-Crafts alkylation, right? We don't have to worry about any rearrangement here. So that's really good. There's no multi-addition. Because the acyl group is a deactivating group. But again, that's not the big deal. The real big deal is that there's no rearrangements here. And then the other thing combined with that no rearrangement is that we can easily reduce our acyl group to an alkyl group. So we can take our acyl group, and then in the presence of some zinc mercury alloy and some hydrochloric acid with some heat, we can reduce it down to an alkyl group. There are other ways to do this reduction. I'm only going to ask about the top way, but in case you have some kind of standardized test or anything like that, another common one is the Wolff-Kishner reduction. And it does the same thing.